of W that allows you to deal with all kinds of generalized inductive definitions. And then let's call this theory in this way. So ML for Martin-Löf, T for type theory. But then I just would like to stress the W because it makes a big difference whether you leave it out or not. And then this little less than omega stands for having these externally indexed infinitely many universes, UI. Well, okay, so that's kind of the Martin-Löf type theory you would find in the book from, I think it was from '84, called Intuitionistic Type Theory. And then you can also add something which actually was considered by Russell and also later was considered in the context of the calculus of constructions. And that's the type prop of propositions. And so there's another type, and this type is then asserted to live in the first universe, U0. Okay. And then, well, how strong is this theory? And this is actually not clear. It also depends on details, how much stuff you put into the type theory. Well, it's not difficult to show that ZFC, say if you have ZFC or even ZF with global choice, and then you add infinitely many inaccessibles, that is enough to model such a type theory. And, well, how about just the Martin-Löf type theory, the full-fledged version? How strong is that? I think it's also, there's no real place in the literature where you find the answer. And another question is, well, so type theory is one thing, and another thing is set theory, and there is a way of relating the two. So this is actually the title of this talk. And so you might want to ask, what are the set theoretic counterparts of these type theories? So such questions I plan to talk about in this talk. Okay. You probably all know that recently the popularity of type theory has risen a lot. So here's a quote. Voevodsky's univalent foundations require not just one inaccessible cardinal, but an infinite string of cardinals, each inaccessible from its predecessor. This is a quote from a recent book from this year, Michael Harris, Mathematics Without Apologies, referring, of course, to an older book by Hardy. And so Michael Harris, he's quite a famous mathematician. He worked on the Langlands program, and I think in 2007 he was a recipient of the Clay Prize. So in this book you find several pages talking about univalent foundations and this kind of stuff. Okay. So here again we have this scenario where you have ZFC and you have this kind of tower of infinitely many inaccessibles. And here it sounds like you really need them. Well, I mean, this thing with ZFC plus inaccessible has come up a lot. Well, if you recall maybe Weyl's theorem or Fermat's last theorem, then if you go back, if you want to write down a proof of all the details, all the things he draws on, then there's also Grothendieck universes, and they're also modeled via inaccessibles. But as you probably know that in recent times, people have been trying to lower the requirements, and now I think it's down to third order arithmetic or even piano. So for instance, Angus MacIntyre has sketched a proof in piano, and other people have worked in higher type theory or second order, third order arithmetic to do it. Anyway, I'm going to talk about intuitionistic set theories, and so I'd like to add a few words you might consider propaganda, but it is kind of strange that each time you talk about something intuitionistic that it will conjure up lots of cliches. So I've listened to talks recently, and so people repeat the same cliches about intuitionism, about Hilbert's formalism, and so on. So just a little bit about intuitionistic theories. Well, the usual take is that this might have some philosophical reasons. This is not considered to be a very strong reason these days if you look into, philosophy departments. So Michael Dummett died just a few years ago, but I think there's no real follower or anybody who kind of takes the same viewpoint as Michael Dummett did. Okay, so if we're not interested in philosophy, then there are other reasons. So one reason, of course, as you know, is that if you have intuitionistic proofs or constructive proofs, you may be able to extract information from them, computational content. Okay. Then there's the reason that actually there's not only classical worlds, there's other worlds, and for instance like topoi, and the internal logic of many of these topoi is not classical. And this is related to the to what one could call, and has been called by David McCarthy, for instance, axiomatic freedom. You might want to adopt axioms that are nice and beautiful and make your life easier, but they might actually contradict classical reasoning, maybe something very basic like the law of excluded middle. And well, for many people this is kind of the line, but this is where they draw the line. They say, okay, if I cannot use classical logic, then it's not for me. I mean, I've heard this many times. They say, okay, I'm probably too old, because if I had to learn how to reason intuitionistically or constructively, that would be very difficult. And I can understand that. Okay, axiomatic freedom. So if you fantasize about this, you can say, well, wouldn't it be lovely if certain things held? Like if, for instance, we didn't have non-computable functions. And if, for instance, those non-standard models of PA didn't exist. And well, this is possible. You can realize this dream. Other things, so for instance, Brouwer proved that all functions from the reals to the reals are continuous. And yes, you can create a world where this is the case, and also other Brouwerian principles are valid. You might also want something like if all functions between manifolds are differentiable. Yeah. So, for instance, engineers very often use something like in the computations they use nilpotent elements. So if you have something h, you take an h which is very small, then you make some calculations, and then in the term you have something like h squared or h cubed, and say, okay, this is basically zero, so it's nilpotent. And this kind of reasoning can also be very useful. Leads to synthetic differential geometry. And well, you can also have something like a set A, which is infinite. Actually, the numbers are injected into it, and A is in one correspondence with its function space, the space of all functions from A to A. This is classically not possible, as Cantor knew. And you might want to have that all functions from the reals to the reals are measurable. Okay. Well, it turns out that you can realize these dreams. So this one here is well known. So if you can have all sets of reals Lebesgue measurable, you have to sacrifice a little bit. You have to sacrifice the general axiom of choice. And for instance, if you in Alain Con's book on non-commutative geometry, he makes this assumption. for some chapters, which just says from now on we assume that everything is measurable. And it makes your life easier. Okay. Now, in this case here, we don't have to give up classical logic. In the other cases, one would have to give up classical logic to materialize this dream. And one way to find such worlds or models is by a technique called realizability, going back to Kleene, and then it has been developed for a long, long time. So one scenario is you start with something called a partial combinatorial algebra, or also known as a Schoenfinkel algebra. So Schoenfinkel in 1924, he was thinking about the basic building blocks of logic. So something you would usually not consider, like how you deal with syntax, how you make substitutions and syntactic operations. And this led to the notion of a certain algebra where you can also do recursion theory. And if you take such a thing, a partial combinatorial algebra, then you can define a universe of sets. So you don't define it in stages. This script P here means power set. And this is just the underlying set, so the carrier of the partial combinatorial algebra. And so this is the construction you do. And basically, so these elements are the elements of this world. They are sets of pairs where the first component comes from the partial combinatorial algebra, and the second component lives in this world as well. A certain similarity to forcing, and then you do then you define a notion of realizability, which there's also similarities to forcing. Basically, so for each so if you take a formula, say in this case of set theory, and you take elements from this world V of A, and you have an element E of the PCA, then you define the notion that E forces or realizes phi of these AIs. And so in such worlds you can realize some of the dreams on the previous slide. Okay. Now, type theory. Okay, type theory is in some sense a very old subject. So types are, say, structured collections of objects such as natural numbers. And then the birth document of type theory, maybe it was 1908, Russell, mathematical logic as based on the theory of types. And then he developed this with Whitehead and Principia. An interesting thing is that also in Hilbert, in his paper on the infinite, there's an appendix where he tries to prove the continuum hypothesis. And this is actually an interesting piece. In it, he actually develops a transfinite hierarchy of dependent types. And there's Church, the formulation of simple type theory, and De Bruyne, automath, and then beginning with the early 70s, Per Martin Löf developed a theory of types. Okay, so this is just history. So focusing on Martin Löf type theory, so he has the notion of judgment, and there are 4 kinds of them. So the first is that something is a type, or A is a well-formed type. Then there's a judgment that 2 types are definitionally equal. And so A, little a, colon capital A, means that this little a is a well-formed term of type A. And then also that 2 terms are of the same type and equal. So these are the 4 types of judgments. And then, well, how do you develop then mathematics and type theory? Well, you need certain type-forming operations, and here they are. So there's the usual stuff. So this is the type of Booleans, the empty type. Then you can create lists over a given type A, the disjoint sum of 2 types. There's the identity type, which figures prominently in this in the univalent foundations in homotopy type theory. This is the dependent product type, the dependent sum type, and WX stands for the type of basically well-founded trees over the family of types BX, X, colon A. And so W types allow you to capture basically all types of recursion that you might be interested in, or say all types of initial algebras. And well, if you can of course view these things as set theoretic objects, and then this is the usual stuff. Yeah, so this is basically a disjoint union here, and then the product type means, well, you look. So what you have is you have kind of a family of types indexed over A. For each X and A, you have a type BX, and then then this product type here is inhabited by all the functions from A with domain A, such that for X and A, f of X is a BX. So there's a straightforward set theoretic reading of all these things.
What is the set theoretic type?
The tree type, well, so inductively, so the rule is that, so if I have this abbreviation, then you have a rule basically if you have something in A and you have a function that goes from BA into W, then you get that sup AF is in W. So it's an inductive definition where this is the clause, how you create new elements. Yeah. And you can read it set theoretically, so then this would be a function that goes from BA into W, and then you create a pair consisting of this of the index. You need to know the index for the domain of the F, and then put the F there. Yeah. So this is one way. And then the type of natural numbers, of course. Okay. Now, in type theory, you don't have to. So usually, when you do first order logic, you first do the symbols, and then you say what are the terms and the well-formed formulas. So here in type, and then you do the basic. So with the well-formed formulas, one introduces the logical particles, the conjunctions, disjunctions, and the quantifiers, and so on. So here in type theory, these things can be represented via the Curry-Howard representation, and so basically the sigma type can be used to represent existential quantifier, and so on. Pi type for all quantifier, and then the product type to represent and so on. So this is the usual way. Okay, and then there's also this identity type. So the idea is that you have a type capital A, and you have inhabitants of this type A and B, and so then this new type ID A, little b, is to represent equality on A. Okay, then there's universes. So what are universes? Universes are types, of course, in type theory, but they are somewhat large types, and they themselves are inhabited by types, and they're closed under taking certain type forming operations. So for instance, this just is as a rule way of saying that a universe is closed under product types. So if you have already a type A in U, and you have a family of types indexed over A, such that BX is also a type in U, then the product type is in U. So in some sense, like it would mean this is similar maybe to a regular cardinal, or even inaccessible. Okay, that's a universe, and then using this notation here, so if there's a subscript 0 means no universes, and n means we have, I think we have n minus 1 universes. Okay, so what's the strength of this type theory. And well, I think there's no place in the literature where you find this question addressed.
Type theories also with prop as before?
No, this is without prop. If prop comes into play, it's indicated. It will be indicated. Yep. Okay. So Martin-Löf type theories, there were a lot of investigations, mainly in proof theory, in the starting in the say late 1960s, and then in particular in the 1970s. And if you vary the ingredients of these type theories, you get very different consistency strengths. There's also a way of having Martin-Löf type theory without universes, which is just of the strength of piano, for instance, or even less. And so one considered different types of universes, not just these kind of straightforward universes, but also universes that somehow model what is a Marlow cardinal, for instance. And the strength of these type theories was computed exactly. So meaning in terms of either other theories, so this is proof theoretically equivalent to a well-known theory, or even in terms of proof theoretic ordinals. And just to give you a flavor, just look at this particular version of type theory here. So ML, this has the one indicates it has just one universe, and then it has the usual stuff, but not necessarily W. And then this little W here as a subscript is supposed to indicate that just the universe is closed under W types, but not the world of types at large. So you can also build, so if you have a universe, you can build large types on top of the universe. So here the restriction is that only the universe itself is closed under W types. And then this theory here can be matched to a fragment of second-order arithmetic, namely delta 1-2 comprehension plus bar induction. So here at least you see that these theories are not weak. I mean, weak if you compare it, for instance, to the usual scale from reverse mathematics. It's above that scale. Yeah? Now, so there was work by, so Eric Palmgren started embedding certain theories of iterated inductive definitions into type theory that gave some lower bounds. And then Anton Setzer and I, we computed exact bounds. So the exact bound for the full Martin-Löf type theory with all the universes and all the W types can be expressed as follows. So you have, so one way is saying this is of the same strength as Kripke-Platek plus n many recursively inaccessible ordinals. Or another way is by saying, well, this is some base theory plus there's an n tower of beta models of delta 1-2 comprehension, where n varies over the naturals. So that's the strength of the full theory. So there's two tasks to it. Namely, the first is you want to show that the type theory is not stronger than any of these theories. So this is a task of modeling type theory in those theories. And the other task is to show that actually the type theories have the same strength. And the only way I know to do it is via ordinal analysis. So basically there's an ordinal analysis of these theories, these classical theories here, and then one can show in the type theory that the proof that you can climb up to the proof theoretic ordinal within type theory. Okay. And then, of course, the upshot is that the strength of all of these type theories is well below pi 1-2 comprehension. Well, there's, of course, this very recent addition to type theory, the univalence axiom, which takes the identity type seriously and says something about the identity type on universes, that somehow identity and equivalence of types should coincide in some sense. I'm not going to define this. The question is, does this axiom change the picture? So from the quote by Harris, so he said you need, well, in the quote it says, it insinuated that you need inaccessibles. Do you need more for univalence? And well, the question currently is somewhat open, but the conjecture is that you won't need more proof-theoretic strengths. And this is due to recent work on the cubical set model for univalent type theory by Besem, Coukon, and Huber. And this can be done constructively, so it can be done in type theory itself. Though at the moment it has not all type constructions have been included, so this is still not a done task, but this is quite indicative that univalence will not add any strengths to it. Okay. All right. So much for the usual stuff. Univalence I'm not going to talk about. So now back to the type of propositions. Well, Russell was very concerned about impredicativity or vicious circles, and he didn't want to allow impredicative constructions. And so he said that in this quote it says that that statements about all propositions are in some sense meaningless. By saying that a set has no total, we mean primarily that no significant statement can be made about all its members. In such cases, it is necessary to break up our set into smaller sets, each of which is capable of a total. This is what the theory of types aims at effecting. So he had this ban on these impredicative definitions. The lesson to take from this is, so we must be careful about introducing the notion of proposition. And there are predicative approaches to this. So in Principia, one has these kind of level restrictions, and or one looks at smaller collections like in Martin-Löf type series, where the smaller collections are universes. One can also stick to the full impredicativity, but then there are certain restrictions. You have to obey certain restrictions on the type-forming operations. For instance, in system F. On the other hand, so Russell erected this taboo on impredicative definitions, but on the other hand, probably entirely for pragmatic reasons, he re-allowed them, if that's an English word, through the back door. And so he introduced his axiom of reducibility. Okay. So now with this type of propositions, you can do interesting things. So it's already a long time ago that Russell wrote a paper that was in 1903 and 1906, so predating type theory, where he talked about defining certain logical operations in terms of other operations, namely that you can define and or negation and existential quantifier in terms of just the implication and universal quantification. But you need quantification over propositions. So you need this for all P, and this P is a quantifier over all propositions. And so, for instance, there is an impredicative way of defining conjunction in this way. So you say you define phi and psi to be, for all propositions, if phi arrow psi arrow pi P, then P. And you can do this with the other quantifiers and conjunctions. Connectors, I mean, in this way. And so I think this idea was then taken up by Pravitz in 1965. And so if you work in second order intuitionistic logic, then you can define everything in terms of arrow and universal quantification. In a certain sense, this means if you look at these things that you define the connectives and or negation and existential quantifier inductively. This you can view as an inductive definition. Okay, so the type prop allows you to do to define these operations in terms of just the fragment arrow for all. And this idea was used in Girard's system F and in the calculus of constructions. And it's also a standard way of representing logic in the type theory Lego and in Coq. And well, and Coq is actually is quite a well-known proof assistant. And since the type prop figures in Coq, it would be interesting to know actually how strong the type system is. Now, what's the central rule for prop? Well, there's different versions of it, and I will show you different versions. So one version is this. So to characterize prop, this is here written as a rule in natural deduction. So so this gives the inductive clause for defining the type prop. So the situation is here, so we have some context gamma. So this is actually this is a sequent calculus rendering of it. So we have a context gamma, just ignore this. So if you can show that for each x in a type A, that then B of x is an element of prop, then you conclude that the dependent product type Px colon A Bx is also in prop. And I mean, this rule is somewhat surprising even from a classical point of view. Why is it surprising? Well, I mean, there's no restriction on this type A whatsoever. So you have a type universe and you have this type prop, but then you build stuff on top of prop. So this could be, if you view this set theoretically, so this could be any set A here, and then you have basically a function going from A into the union of the B axis here, and then you say this product, this product, dependent product set of all functions with domain A, such that for x and A, f of x is in Bx, that this is an element of prop. So you would actually, even classically, you would run up against the problem of size, because this A here is quite big, and if you do the usual way of representing the product type, then it's just not possible to squeeze all of these things into one set, prop. But there's a trick how you can do it. Okay. So here's how you model it in classical set theory. It's very easy, actually, once you see it. Prop consists just of the two things, 0 and 1. And then for a function f, you define you represent it in a non-standard way, as it were, not as a set of ordered pairs, but in this way. Yeah. So f is a traditional set theoretic function. It's a set of ordered pairs, but then you associate it with this object lam of f. Yeah. And from
stand for something.
Yeah, it stands for something, but it escapes me right now. Okay, and then what you can do is, now, if you have, you can represent these kind of dependent products in a kind of a non-standard way. So if you have an f that goes from A to prop, then you define this product in this non-standard way. Instead of taking all the f's going with domain A, you take the lambs of that, lam of f. And then you see what happens is, so classically, So this f is something that goes into prop, okay? So either f of x is 1 for all x in A, and then you see then this thing here, this set theoretic object is just singleton 0, yeah? Or you have that fx is 0 for some x in A, and then this is just the empty set, yeah? So that's the way how you can model it in classical set theory. So hence, hence these products are in prop. But as you see, you need classical logic to do this here, because you make this case distinction here, either or. Okay, now some other ways of representing prop. So let's use this notation here. So here we have, say, two types, and we have arrows in both directions. So this means that this f is a pair of functions, f1 going in one direction and f2 in the other direction. And then you can write things like, okay, this is supposed to mean that there's basically a bijection here. In that sense. And then you could introduce maybe other versions of prop or other versions of Russell's reducibility axiom. So you could, for instance, have a type P sub red not for the color but for reducibility. So you say that this is a type that lives in the first universe, and everything in this type is a code for a real type, but a type that lives in the first universe U0. And then you have this rule. This is the crucial rule. So if you have any type anywhere in the universe, so this could live in this type A could be the 27th universe. So something that could live high above the first universe. Then it has some counterpart in the type P red. And so the counterpart is just the A between these angled brackets here. And then what is the relationship to between basically this kind of representation in P red and the original thing, that you have some kind of function that goes both ways, yeah? A pair of function that goes both ways. Yeah, and well, this is a type theory which is, if you introduce such a reducibility type here, it's pretty strong. So this has at least the strength of ZFC. And you see there's some kind of, this kind of embodies classical logic and also choice in some sense, because, well, this A can be very big here, right? So this A can be very big, and since all so the T red of this angled A, that's an element of the first universe, so it cannot be arbitrarily big, yeah? Okay. And so that means that you will have to make a choice somehow here. You have to cut this A down to something sizable. Then there's a version that is closer to the original prop that I showed you on the first page, where you have this closure under these dependent types. This is kind of a negative version. So here, another candidate for reducibility of types, P double negation, lives in the first universe, and also everything in it decodes to a type living in the first universe. And then whenever you have an arbitrary type A, there is a code in P double negation. And then this is the relationship here. You can go back and forth between the two. Well, not quite. You can only go back. You can go back and forth between the decoding of the representation here and the double negation of A, and this makes a big difference intuitionistically. And it turns out that this way of doing reducibility of types is equivalent to the type prop, basically. Okay. Okay, so here a little bit more about these prop. I haven't stated all the rules. So one rule I haven't stated so far, I think, is, okay, so there's, first of all, you need something that goes into prop, otherwise it's empty. So the empty type is in prop. And then also, if something is in prop, yeah, So here I use the version where the elements of prop are real types. Yeah. And so if something isn't prop, then okay, it's a type, and then you can ask about, well, what kind of elements can it have? And this just says that, well, all the elements are identical. Yeah. They are proof irrelevant, as one sometimes says. Okay. So the question about how strong this Martin-Löf type theory with prop is still open. A more manageable question is the following. If we don't ask too much, we just ask for prop to reflect certain types, namely only types that live in the first universe. So that's a severe restriction here. Yeah? So we have the same setup basically. So prop is in the first universe, empty is in prop, and then comes the restriction. The restriction is now that these dependent products only belong to prop if the index set for the product is an inhabitant of the first universe. Okay, and then the other stuff. Okay, so if one has this restriction, then one can say how strong the type theory is in terms of set theories. Okay, now to the thing moving between types and sets. Well, and that's actually a nice way of doing this. And there's actually an easy way how you model type theory and set theory by just viewing these product types as the real dependent function spaces and so on. So that's an easy way of doing it, except for this little problem with prop, but I showed you how to solve that. So types can be represented as sets. So then we have an embedding of type theory into set theory. But there's also another way around, and you can embed set theory into type theory. And this was engineered by Axel in the late 1970s. And this is the sets as trees representation. So the sets are represented as trees in type theory. And then you get an embedding, or you get an interpretation of set theory and type theory. But what is crucial, actually will be crucial here, that it usually only works for intuitionistic set theory. So this interpretation here, the set theory usually has to be intuitionistic, unless you have a very strong version of the reducibility axiom, like P rad, for instance. Okay, and well, going back, well, what kind of set theories will actually crop up when you do this? And this was, to some extent, was Axel's question. So constructive set theory, or these constructive set theory and intuitionistic set theories were first considered by Myhill, also in the 1970s. And Peter Axel was interested in seeing whether Myhill's constructive set theory could be interpreted in Martin-Löf type theory. And that's how this interpretation came about. And, well, so here are some intuitionistic set theories. So the first one is called intuitionistic Zermelo-Fraenkel set theory. And this has just the usual axioms, except for some changes. One change is that instead of the foundation axiom, you have to state it in a positive way. And you better strengthen replacement to collection, because the replacement says for all x and a if there's a unique y, then you can collect these y's. But the situation is in intuitionistic set theory, having a scenario where you have for all x and a you have a unique y is rather a strong assumption. So you better relax it a little bit. And so this is one intuitionistic set theory. And it turns out that this is of the same strength as ZF. So there was some kind of interpretation done by Harvey Friedman, which involves a double negation interpretation. But in connection with Martin-Löf type theory, other intuitionistic set theories will crop up. And this is constructive Zermelo-Fraenkel set theory, CZF. And so here are the axioms. So the main changes are separation is restricted to bounded separation. And instead of the power set axiom, one has an axiom called subset collection, which says basically that if you have two sets A and B, it first says that then the collection of all functions from A to B is a set. This, by the way, is intuitionistically, function spaces and power set are totally separate animals. And this subset collection axiom is some kind of a relaxing of that condition. Not only all the functions from A to B, but more from the set. And then collection here even has to be strengthened. So since that means that if for all x and a you have a y, then you would like to collect enough y's into a set B, but you don't want B to have rubbish in it, so everything in B should relate to some x and a such that this holds. If you don't have full separation, then you need this extra requirement. You wouldn't get it for free otherwise. Okay, so that's constructive CZF. And then the interesting thing is so this is just, what I showed you. CZF is basically the counterpart to Martin-Löf type theory, the set theoretic counterpart. But if you add the type prop, you might still look at the axial interpretation and see what kind of set theory can I validate in that way. And then all of a sudden you get some strange things. So it was, I think, first observed by Nicola Gambino. But one thing is you get negative separation. This negative separation also showed up in a manuscript by Beeson in what he called it negative IZF. And you get not power set, but you get the negative power set. Yeah? And so these axioms are somewhat results of interpreting the type theory with prop. Interpreting set theory into the type theory with prop. Okay. So this gives rise to a theory called negative intuitionistic Zermelo.
What is the negative power set axiom?
Double negation is crucial.
Well, what it says is you cannot collect, so this means, this part here means x, so x is a subset of A, right? The usual power set says that you can collect all the subsets of A into a set Z, right? But here you can only take those subsets that are in a certain sense stable. They obey a stability condition. This is, intuitionistically, this is a very strong condition here, because if not u and x implies u as an x, so this basically, this has almost no information, this here.
Why is it called negative? Not much negative there.
Well, you put, okay, so this is called negative because you put negations here, right? And here you also have negations. Call it like you want.
It's two negations.
Well, it's double negative power set.
Michael, double negation is different from negation.
What did I say? Oh, yeah. Oh, no. It's somewhat negative. By the way, I didn't coin the names, so the names were already there. Okay, so then we get negative intuitionistic set theory. And so what are the restrictions? Well, you have to restrict separation to bounded separation. But then we have negative separation, and we have negative power set. And the usual stuff. Okay. And then, so this is a set theory, an intuitionistic set theory that shows up when you do the sets as trees interpretation in type theory with prop. Well, and then of course the question is what do we know about such negative versions of IZF? Are there models where we can separate IZF from negative IZF? And what's the strength of negative IZF? Okay. And right, okay, First, I'd like to answer the question about, so there's this restricted version of prop, where the where the prop rule, where these dependent products, you can only say they live in prop if the index set belongs to the first universe. Okay, and it turns out that this version of prop, this restricted version of prop, is related to power cryptoplastic set theory. Now, power cryptoplastic set theory is an extension of cryptoplastic, where you take the notion, where you take certain quantifiers, namely bounded quantifiers of this form here, so subset bounded quantifiers, you view them as bounded quantifiers, and then you have a different notion of boundedness, and that's your cryptoplastic. Yeah, then you have separation and collection for this, for the class of bounded formulas, where bounded is taken in the sense of, well, the usual bounded quantifiers, but also subset bounded quantifiers. Okay, so this is a name for power cryptoplastic. By the way, it's not the same as just taking cryptoplastic and then adding the power set. That's a much weaker theory. Okay, I don't want to talk about this. So now the same strengths, what do we have? Well, power cryptoplastic set theories of the same strength as certain other things. You can add the GAC stands for global choice, so you have a global choice function. It's of the same strength as CZF plus power set, and interestingly, it's of the same strength as this particular type theory here. So where you have one universe, you have the type of trees over this universe, and you have the prop, where prop reflects types just in U0. Okay, and there's also something about negative power set. And so the exact strengths of all of these theories coincides. And the interesting thing is that to get the full thing, one needs something like ordinal analysis.
This BH, tau belongs to BH.
Yeah, that's the ordinal analysis part. This BH stands for the Bachmann-Howard ordinal. So this means all of these theories and can be characterized in terms of Z, which is Zermelo set theory. But then Zermelo set theory, where you can iterate the power set operation, but only below the Bachmann-Howard ordinal, BH. The Bachmann-Howard ordinal is basically the proof theoretic ordinal of the theory of one inductive definition, the same as the proof theoretic ordinal of actually CZF and cryptoplastic. So this needs some kind of ordinal analysis in the presence of a power set. Okay. So now the strengths of IZF in the negative way, negative IZF. Well, it turns out it's not much stronger than the previous theories. It is of the same strength as, well, if we take Martin-Löf type theory, we have just one universe. We have the type of trees over this universe, and we have prop, but prop now in the unrestricted sense. Yeah. So the index set in that case could be any type, so a type which lives way above the universe. Okay, and it turns out that this theory is much weaker than ZFC or ZF. And the strengths can be characterized in terms of Zermelo plus iterations of power set. You have to go beyond the Bachmann-Howard ordinal, but not that much. It depends also on other ingredients. Okay, so here we have a set theory, this kind of negative IZF, which has actually a much, much lower consistency strength than ZF. Just to come back to the first thing about wouldn't it be lovely, there's actually, you can actually create models of a negative IZF. So models of negative IZF which are not models of IZF, yes. And I only observed this recently, so Andrew Swan, he wrote a nice thesis in 2012 about realizability models and automorphisms. And so he looked at realizability models over PCAs. And the interesting thing is, well, the PCAs are usually sets. These partial combinatorial algebras or Schoenfinkel algebras are sets. And but he looked at the scenario when the algebra is actually a proper class. Yeah. So this is maybe there's a certain similarity to class forcing. And it turned out that class realizability over VA, where A is a class, well, it actually works. And then the question is, well, works for which axioms of CZF? So it works for all the axioms of CZF, so in particular for strong collection and subset collection, all of these things. But there's a problem with bounded separation. So in general, it does not work for bounded separation. So this VA might not realize bounded separation. But it turns out that one can impose an extra condition that he called uniformity. And if you have this uniformity, then V of A validates also bounded separation, so full CZF. And but it turns out that in this way you can reject or find a model that refutes power set, even if the background universe satisfies power set. And this can be done as follows. You basically view the whole set theoretic universe as a bunch of constants. It's just constants. So every set is a constant. You cannot look inside it. So you have just lots of constants, class many, and then you build a lambda calculus on top of it, where these constants are just atoms. And then one has a notion of beta reduction for these terms. So you have class many terms, you have beta reduction, and then you mod them out by beta reduction. And this gives rise to something which is called an order PCA. And it turns out that, well, so he showed that this particular class realizability, it realizes CZF, but it refutes power set. And then I looked at it again, and it turned out, well, actually, although it refutes power set, it validates negative power set and negative separation. So here we have actually a model which separates the two. Okay, so the big question still is, if we take the full system prop with all the universes, how strong is it? And so here we have there's a connection between this type theory with all the universes, with prop and so on, and an intuitionistic set theory. We know that they are of the same strength due to Axel and Gambino. And this is IZF negative, and here this extra stuff means you have universes, so basically inaccessible. But there's still work to be done to determine what is the exact strength. Thank you.
Are there questions or comments?
In that last sentence, is prop U omega a mistake for prop U less than omega?
Yes, it's a mistake. Thank you.
Are there any longer questions?
All the theories you've been talking about so far are no more than ZF plus omega many inaccessibles. Set theorists have been looking at theories of much stronger consistency strength than that, in whole large cardinal stuff. Are there any proposals for how to include not large cardinal axioms, but things of equivalent consistency strength in the type theory?
By equivalent consistency strength, do you mean the real classical strengths of large cardinals? Well, I mean,
or constructive.
Yeah, I mean, so there was a lot of work in the 90s on type theories, Martin-Löf type theories, augmented by stronger universes. So there was something like, I think Eric Palmgren started with super universes. And then Anton Setzer and I, we looked at things like Marlow universes. And also Anton Setzer then studied these kind of universes that correspond somehow to the constructive counterpart of weakly compact cardinals. So there is work on that scale. But it hasn't, I mean, you could combine it now with the prop and see how strong it is. But whereas we know how to deal with, say, the full Martin-Löf type theory plus Malloy universes and so on, we know how to deal with that because everything is in the scope of techniques from ordinal analysis, from proof theory. Yeah. But the problem is, as soon as you add prop, you have these versions of negative power set, and usually it's very difficult to deal with that proof theoretically. So somehow you can do it for some initial cases, but the proof theory has not been developed to do this. So I think it would be very difficult to do it.
What is the height of this Bachmann-Hour, the ordinal? Is it a cardinal or is it
very high.
countable?
Little tiny countable thing.
It's countable. It's a recursive ordinal.
I see, so it's
It's
below
smaller
omega
than
1.
omega 1 Church Kleene. It's you can write it down as a. You can prove many.
Borel determinacy would that be much?
Oh, yeah.
than all these theories?
That's way beyond. No, wait. What do you mean? The theories?
I mean, if you take IZF plus Borel determinacy, what
You mean full IZF plus Borel determinacy? Well, that's of the same strength, because Borel determinacy is provable in ZF, and IZF is of the same strength as ZF.
IZF double negation?
Oh, double negation. Yeah. Difficult question.
But first you have to define Borel intuitionistically. And if you survive that, then you can go on.
Yeah.
Johan, did you have a question?
Yeah, about this negative power set. Is it related or close to something that would be called desirable power set axiom? If you take subsets, you collect together, or subsets which are desirable in some sense.
Well, they would, of course, be in the negative power set, but decidability is a very, very strong requirement. So basically, the power set for decidable subsets, you can already, that this forms a set, you can already prove this in CZF. You don't need it as an extra axiom. That's very strong. I mean, the requirement to be decidable is very strong.
Well, ordinal row, is that countable?
Who?
The ordinal row you mentioned.
The one that gets blown back in half.
Oh,
Yes.
yes.
Right, that's what that.
Yeah, it's also countable. Where did I have this?
One you said was just a
It's
little
not-
bigger.
Not much bigger.
Yeah.
than,
This is not considerably bigger.
Oh.
Not considerably bigger than a countable ordinal. You're
So
countable.
it's not much.
Can I ask also to show that you show the slides on the homotopy that you passed over?
Well, that's just a bunch of definitions. I really want to see.
I
Okay.
will do it later on.
All right. How do I find this?
So, and this cannot be attacked with the techniques that you spoke about?
No. I mean, the story is different there. So the guess is that univalence doesn't add anything in the way it adds a lot, but not in the way of proof theoretic strength. And the argument was based on the idea that this original model, Voivodsky's model based on simplicial sets, used a lot of set theory in the background, inaccessible. Yeah. But now there is this constructive version of it, the so-called cubical sets, and they do it in type theory, in the ordinary type theory itself.
But
And,
the
and this
model-
shows that what they have done so far doesn't add any strength. But they haven't dealt with all the type constructions yet.
But in the model with the count of remaining accessible cardinal, you can code all kind of types that you can conceive.
Yes.
Way at the beginning, when your slide was, wouldn't it be nice? One of the options you mentioned was every function, or equivalently every set of reals was Lebesgue measurable. And you said, well, you can realize that even with classical logic. Solovey's construction gave us that. Is there a natural constructive model where all sets of reals or all functions are Lebesgue measurable?
I wouldn't know. Well, you know.
So Alex Kreutzer wrote a paper on this. It's still all classical, but it goes much more down. It's at the level of AC0 plus or something.
I mean, the interesting thing is that in set theory you really need something like inaccessible to do it. And you say that there's a way of...
So Alex Kreutzer wrote this paper where you can get that all sets are measurable somehow, but you have to look at the details. It's rather weak in fact.
Mhm. Wow.
Well,
I
maybe
suspect that people are rather eager to attack the coffee, so maybe we should continue the discussion while drinking coffee. Let's thank
maybe it's easy to
and we begin again at 11:30.